Thanks a lot to the organizers, Nuria, Lydia, for putting together this very nice event. It's cool. And I'm very happy to speak here. And as Lydia already announced, now we're going to have a shift of topics. So we're going to talk about reference frames. And Anne-Catherine and I shared the topics. So these lectures are like more or less coordinated. And we will build up, starting from really like the basically Galilean quantum mechanics, so third-year quantum mechanics that you see at university. And progressively, we're going more towards gravity. And then Daniele will kick in, and he will tell us about quantum gravity. So the topic is quantum reference frames. So to understand what quantum reference frames are, we should first understand what reference frames are and why they are important. And roughly, we can say that reference frames and coordinate systems are essential to fix the point of view from which observations are carried out. And so in these lectures, we're going to talk about reference frames and coordinate systems. We will put them on the same level, but be aware that there are differences in the literature, especially concerning whether we associate observers to reference frames or not. And for us, we are not going to consider the topic of observers associated to quantum reference frames at the moment, because, well, it will become clearer in the following, but then basically we immediately jump in the Wigner's friend situation, as Renato and Yile have talked about already. And we want to distinguish the two sets of problems. So we will just not deal with those type of situations, even though they're very, very relevant for what we're going to talk about. So for what concerns these lectures, basically, a reference frame is a set of variables that is associated to a physical system. And we can use this set of variables to describe other physical systems relationally. And the relational aspect is going to be extremely important for what comes now. And it's something that we import basically from both from operational considerations and from general relativity. So the history of quantum reference frames started in 1967, when there were two papers in the same year from two different communities. So there was a paper in quantum gravity by Bryce DeWitt, which introduced reference frames as material physical systems. And so basically, the need to use some field, some material field, so not gravity, material as opposed to gravity, to define relational observables in gravity and, more in general, in quantum gravity. And from this paper, the whole literature of quantum reference frames in quantum gravity was derived later. And it followed its own path, and maybe Daniele will say something more about this. I don't know. Yes, OK. There was, in the same year, another paper from Aharonov and Kaufer, and then Aharonov-Susskind, that instead introduced reference frames in quantum information. And this also started a whole set of literature in the quantum information community that also took its own path. And the funny thing is that these two research directions remained parallel for many years. And now, just recently, in the recent years, there have been many interactions between the quantum gravity and quantum information community. And so there is so convergence is starting to be achieved in these two different approaches. And so although basically the two research lines proceeded in very parallel and independent ways, there was a common core in the need of associating reference frames to physical systems and in the relationality of the description. So these are things that in both communities were considered to be extremely important and that each community has implemented in its own way. OK, so just to give you an idea of the flavor of the type of research that one can do in quantum reference frame, the historical approach to this question. So in quantum information, the typical scenario concerns two systems A and B, so two players, you can consider them. and they need to share information, but they do not know how they are related relative to each other. So imagine like A is here, B is there, they cannot see each other, and they're confined in their laboratories. And they do not know, for instance, what is the z direction for each of for the other one. They know what the z direction is for them. They do not know what it is for the other player. And then they want to identify this. Say, imagine Alice wants to say, okay, I have this physical system that I can prepare, and for instance, it's a big spin, and I point this physical system in my z direction and to communicate to the other player what the z direction is for me. And they want to encode this information and then basically make the communication channel as good as they can, so that the other one can learn what the z direction is for the first system, for the first player. And clearly there is some quantum uncertainty that is associated to this big spin because it's a physical system, so it's not a perfect encoding of the direction. And so there is some quantum uncertainty. So this is a typical scenario that was considered in the historical literature on quantum reference frames in quantum information. On the gravitational side, and here I will just say just a few words because Daniele then will pick up. So the general flavor of the discussion is that if gravity is not classical, but it is quantum, then we don't have a classical spacetime. And if we have no classical spacetime, we have no way of defining a classical reference frame. So, as I mentioned, there is this important relational approach in general relativity. So the idea there is that if I have a single system in the whole universe, it doesn't make sense to talk about the localization where this physical system is, because I have no other reference to localize it. I need at least two systems in general relativity to make sense of localization. And now, what we want to do is to consider the relative localization between two material quantum systems in whatever replaces the spacetime when gravity is quantum. So whatever will happen to spacetime, so we can think of some quantum spacetime, some very wild notion of this type, then in that case, the localization should be taken with, basically relative to two quantum systems that are in this more general structure. And there is also some, so this is a more intuitive picture. There is also a more technical motivation for introducing quantum reference frames in quantum gravity that has to do with the quantization of gravity as a gauge theory. And Daniele will talk more in depth about this type of problem, about canonical quantization. So, what I'm going to talk about in these lectures is instead a particular approach to quantum reference frames that some people call foundational, some people call perspectival. Pick your name. I don't know which one is a good name for that, but it is something. So this is what I'm going to talk about. And you should see these lectures more as a research program. So I'm not going to provide you with final answers to a question. It's more like we're building up, starting from some, it's a bottom-up approach, and we are still trying to build up towards more complicated scenarios, towards introducing gravity inside this framework. So probably you will have more questions than answers after these lectures, but I think this is part of the fun. Okay. So the paper that I'm first going to talk about, I'll give you the reference, is, okay. And this is 2019. Okay, so what is the physical question that we ask here? Imagine we have three physical systems. We have A here, we have B, and we have system C here. And we want to describe these systems relationally. So this means that if I stand in C, I can assign some positions, so say XA to A and xb to B. But if I stand in A, then I assign, okay, these are both blue. Okay, doesn't matter. Maybe I can take this. Is this also good?
Does anyone have green?
Ah, this is a pen.
All of them.
Okay, great. Thank you very much. So basically, this would be QC from the perspective of A, and this would be QB from the position of B from the perspective of A. So now we want to consider the following scenario. We have C, that is our initial frame. Wait, maybe the other one was better, though. A is the final frame, and B is just a quantum system. That they both observe. Okay, so the first thing that we learn is that, so since this is an operational approach, a relational approach, then we only care about relational variables. So this means that if I stand in C, then I will describe the system of A and B, but I will not describe the system C. To be more precise, this is not exactly the right way of putting it. So this means that if I write the quantum state of A and B, what I actually mean is I'm writing the quantum state of the relational degrees of freedom of system A and B relative to C. So it's more the quantum state is more in the connection between myself and the rest of the world rather than associated to a physical system by itself. Okay, and so this also means that if I stand in A, then I will describe B and C, but not A. Again, this is more the connection between B and C with A. So basically, the information that is in the physical system is the same all the time. I'm just reshuffling the information to basically single out my point of view. Okay. So now imagine that we want to describe these relative positions from the perspective of C, and then I want to change it from the perspective of A. So if we look at this diagram, then it is immediate that basically I need to send XB to QB minus QC, and then I have to send XA to minus QC, because you see, here I just have to invert the arrow, and here basically XB is QB minus QC. Okay, so how do I achieve that? So to do that in quantum reference frame, first let us set the stage. Yes? So XB is the position of B relative to C, and QB is the position of B relative to A.
And that Q and X is just doesn't have a meaning, right? It's X or Q, it's
I just changed the
it's not like
label. Yeah, just change the label to distinguish the two frames. Okay, so let us first talk about what is a reference frame transformation just in quantum mechanics. So if I want to do that, so let us consider, for instance, a translation. Okay, so a translation is written as a unitary operator, ut, that is e to the I by h bar minus x0 p, where what is x0 is the amount by which I translate. So we can see that if I have my initial reference frame here, and I move to a different reference frame here, then the amount by which I translate is this x0, and this is a fixed quantity. Or I can also have a boost, a Galilean boost, which I called UG. And this is also a unitary operator, that is e to the I by h bar, v, g, where this G is the boost generator, and it is Pt minus mx. Okay? So in this case, what I'm doing is I'm basically changing the relative velocity of my reference frame. So I'm moving to a reference frame that moves with a constant and uniform velocity from my perspective. So there is a class of transformations that will be interesting for us in the following, and these are called extended Galilean transformations. That are transformations of the type x prime equal x minus xi of t. And they were, so basically the action of these transformations in quantum mechanics was found by Daniel Grimberger in 1979. So it's definitely not new. So I will switch to the green because I think I can write more clearly. So in particular, if you want to implement this type of transformation in quantum theory, so now I'm making the language that Daniel Grimberger uses in this paper more modern. So you can write this as a unitary operator that depends explicitly on time, and this would be e to the minus I by h bar m xi dot of t x e to the I by h bar xi t p, and e to the minus I divided by h bar. Then you have m divided by 2, 0 t ds xi dot square s. Okay, so this looks like a complicated transformation, but in the end you see this is just a function, so this is not an operator. Then here we have the p operator, so it's a translation in position, and here we have x, so it's a translation in momentum. So it's in the end it's not so difficult, and of course you can rearrange these terms differently and you will get an equivalent expression. So now if we start from the Schrödinger equation, so we have IH bar d rho by dt, and of course m is the mass of the particle that we're transforming. D rho by dt is h rho, where rho is the density matrix and h is the Hamiltonian in the initial reference frame. Then it is possible to show that if I apply this unitary transformation to basically on the left and on the right, I still obtain another Schrödinger equation that is d rho prime by dt equal to h prime rho prime, where rho prime is u rho u dagger t, and h prime is u of t h u dagger t plus IH bar du by dt u dagger t. So, and this is actually a very easy calculation to do. You just need to, yeah. Oh, sorry. Okay. So this is actually a very easy calculation to do. You just plug u and u dagger on the left and on the right in this expression, and then just use the Leibniz rule for the time derivative. So if the equations of motion transform in this way, then we say that the physical laws are covariant. And in addition, we say that we have a symmetry of the physical laws if the initial Hamiltonian H, so symmetry, if the initial Hamiltonian H is mapped to a final Hamiltonian H prime that has the same functional form. So what does this mean, that it has the same functional form? So for instance, imagine that we have an initial Hamiltonian that is just a free particle Hamiltonian. Then, if I take a a translation or a boost or a Galilean boost. So basically, a translation is where this, so basically x prime equal to x minus x0, so this is a constant, and so this is the translation, and the boost is x prime equal x minus v0 t. So basically, I have to plug this psi x, psi of t here, here, and here. So in both cases, what we get after transforming is h prime equal to p squared divided by 2m. We can put a prime just to say that this is after the transformation. So you see, this is exactly the same functional form after the transformation. More in general, for if we keep psi of t general, if we start from a free particle Hamiltonian, h, then we end up with h prime, p prime squared divided by 2m, plus m psi double dot of t x. So, in particular, you see that if this is constant, then we get an accelerated frame. And this is exactly what you would get when you transform to a frame that is constantly accelerated from the perspective of your initial frame. Okay, so far so good, no particular innovations. So now, let us imagine that we have an initial reference frame here that we imagine to be centered at the origin of C. And from this perspective, we describe a quantum system, let me just make it larger, B, that has some wave function that is psi b of x. And now we want to move to a reference frame, yes?
Question, so what's the difference between like the unitary of the boost and this external Galilean transformation?
What do you mean? What is the difference?
Yeah, because you have like this unitary of the boost, right, with the momentum and rho and g.
So this is contained. So this is just a general expression where psi of t can be anything. Just pick your like any time-dependent function, and then if I specify it to be a psi t constant, then I get translations. If it is linear in time, then I get a Galilean boost, and if it's quadratic in time, then I get an accelerated frame. And then I can consider higher order polynomials or like even wilder things, and this would still work. But these are three physically relevant examples of the same. So it's just a way to write with the same equation the three different types of transformation that we are interested in.
So that's because it has 1 degree more degree of freedom right time. So
Yeah.
that's
Okay, so now we have this psi b of x that is just any function, and we want to move to a reference frame that is just displaced by some amount alpha from the perspective of the initial frame. So how do you do that in quantum theory? Well, it's very simple. It's just a translation. So we have IH bar alpha p applied to b psi b. And I can write it in position basis as the dxb psi of xb minus alpha of b. Okay, so now imagine that instead of having this very nice, sharply defined function, what we have instead is a system that behaves like that. So, for instance, this is we have a state phi of xa that is distributed according to some wave function, and you see now I want to move, basically I want to center the origin of my quantum reference frame now on this wave function. So if I follow my classical intuition from usual reference frames, then I do not know by which amount to translate. So what is alpha? I do not know what it is, because you see also here I drew it in this way so that there are two peaks. So it's not obvious to pick one point in space to perform the translation and have some well-defined alpha. So what I can do instead is to take seriously the fact that quantum mechanics is linear. And so instead of translating by just some amount alpha, I will translate by all possible alphas on the real line, so by all possible positions on the real line, but then I know that a point here or here will count more than a point here, so I have to weigh the translation by the quantum state of the particle. So basically, if I put this together, what I'm going to do is I have the integral in dxb of psi xb, then I translate by xa, so the position of particle A that acts here, but then this has to be integrated in all xa, because I'm integrated on the real line, and then I weigh the translation on phi of xa, on the quantum system. So basically, this is a way to achieve a translation to the position of a quantum system. So now you can immediately, and then I have to add the quantum state of the system. So now you immediately recognize that when this, basically this xa could also be written as the xa operator acting on this quantum state here. And if I write it in this way, then I can just take it out of the integral. And then this is just the resolution in position basis of the state phi A, and then I have psi B. So what have I done? So look at here. So here I have a usual translation operator where the translation amount is just a number. What I'm doing here is I'm promoting the number to an operator. So basically, alpha goes to x alpha, which means that I also had to introduce a Hilbert space of a particle that I didn't have before when I had just classical reference frames. And this Hilbert space is the Hilbert space of the quantum reference frame. Notice that this transformation is still unitary, so we have no ordering problems in particular, because xa and pb act on different Hilbert spaces. Okay. Then I'm not happy yet, because as I told you, what I have to do is this. I have to achieve this transformation here. So what I did now is I mapped xb in xb minus xa. But now I have to turn this into qc, and I also have to swap the position. Basically, I have to describe the position of A from the perspective of C as minus the position of C from the perspective of A. So to do this, we have to add another operator that we call the parity swap. And we define it in this way. And when it acts on on xa, this becomes minus xc. And when the parity swap acts on pa, this becomes minus pc. Okay. So overall, we obtain that the transformation to just the simplest translation that we can achieve is pac e to the I by h bar xa pb. Okay? Questions up to here? Okay.
So this is done to achieve what translation?
So I'm basically shifting the origin of my reference frame from system C to system A.
Yes.
And basically what I described here. So I started in C. I wanted to shift the origin of the frame in A, but when C and A are described, so basically C describes A in a quantum state, and A hence describes C in a quantum state. No?
I'm a bit confused. So what did we do until now, and why now we need to also add parity? Like, didn't we? Why you weren't happy? Like after the first calculation? Like
after this?
Yes.
Because basically, so if you just calculate the action of this operator on QB,
yes.
on XB, sorry, then you just get XB minus XA.
Ah, okay, you're right.
And now we have to
I
turn
know.
this into C.
Yeah, great. Okay.
Okay.
Nice.
Okay. So, for instance, now let us see some examples. So maybe this will be easier after the examples. So imagine we start with the system XA, so A in a well-defined position, and B in any quantum state. So now, if I apply Sx to this quantum state, then I just translate B by x0, because I pick the position of A, psi B, and then x0A gets mapped to minus x0C. Then, now I can apply Sx to a more complicated state, that is 1 over square root of 2 x1a plus x2a, psi b. So now, for each x1 and x2, I get the result that I have here in the previous line. So what I will get is 1 divided by square root of 2, and then I have e to the I by h bar x1 pb psi b minus x1c plus e. So and I translate by x2, translate system B by x2 when A is in x2, and then this becomes minus x2c. So basically now we see that we started from a state that was a product state, and we get a state that is an entangled state. Yes?
Why is the parity swap allowed? I mean, do we change from from reference frame A to C just by an operator?
What do you mean by allowed?
We go from reference frame A
Yes.
to C.
Well, we go from C to A here.
Okay, but you put the operator on X in A, right?
Yeah.
P in A.
Yeah.
Then you go to minus X in C.
Yeah.
So it's from A to C or not?
So I'm starting from C, and I describe systems A and B. Remember, if I am in C, I describe A and B. If I'm in A, I describe B and C. So here I'm in C, I describe A, and after I'm in A and I describe C.
What is the operator doing? It's just an operator which does that.
So it's a unitary operator, and it applies a parity transformation, so x becomes minus x, because the intuition is that if I see Lydia being in x, Lydia sees me being in minus x. So that's the intuition. And then it's unitary, so it also acts with p minus p, because we give a directionality to our coordinate system, and so if I see somebody with velocity v, they see me as velocity minus v.
So there's also like a Galilean transformation going on.
Yeah,
Also.
yeah. That's the idea. And then we can, I'll give you a third example, that is, imagine that I start from a perfectly correlated operator. So I have x1a, perfectly correlated state x1 plus lb in position basis. And then I have x2a and x2 plus lb. So now you see that the relative distance between A and B is always L. So if I transform using this operator to the quantum reference frame of A, B will always be in L. And then I will have that C is in minus x1c plus minus x2c. So again, here we transform from an entangled state to a product state. So basically, the lesson we have learned is that entanglement and superposition are quantum reference frame dependent. And this is actually quite intuitive if you look at the form of the transformation, because actually the transformation is exactly an entangling operation. So you should expect that this transformation changes the entanglement structure of your total Hilbert space.